The first telescopic observations of Mercury were made by Thomas Harriot and Galileo from 1610. In 1612, Simon Marius observed the brightness of Mercury varied with the planet's orbital position and concluded it had phases, in the same way as Venus and the Moon. In 1631, Pierre Gassendi made the first telescopic observations of the transit of a planet across the Sun, when he saw a transit of Mercury predicted by Johannes Kepler. In 1639, Giovanni Zuppi used a telescope to discover that the planet had orbital phases similar to Venus and the Moon. The observation demonstrated conclusively that Mercury orbited around the Sun. A rare event in astronomy is the passage of one planet in front of another. Occultation. As seen from Earth, Mercury and Venus occult each other every few centuries. And the event of May 28, 1737, is the only one historically observed, having been seen by John Bevis at the Royal Greenwich Observatory. The next occultation of Mercury by Venus will be on December 3, 2133. The difficulties inherent in observing Mercury mean that it was far less studied than the other planets. In 1800, Johann Schroeder made observations of surface features, claiming to have observed 20-kilometer-high, 12 miles, mountains. Friedrich Bessel used Schroeder's drawings to erroneously estimate the rotation period as 24 hours, and an axial tilt of 70 degrees. In the 1880s, Giovanni Schiaparelli mapped the planet more accurately, and suggested that Mercury's rotational period was 88 days, the same as its orbital period due to tidal locking. This phenomenon is known as synchronous rotation. The effort to map the surface of Mercury was continued by Eugenio Antoniadi, who published a book in 1934 that included both maps and his own observations. Many of the planet's surface features, particularly the albedo features, take their names from Antoniadi's map. In June 1962, Soviet scientists at the Institute of Radio Engineering and Electronics of the USSR Academy of Sciences, led by Vladimir Kotelnikov, became the first to bounce a radar signal off Mercury and receive it, starting radar observations of the planet. 3 years later, radar observations by Americans Gordon H. Pettingill and Rolf B. Dice, using the 300-meter Arecibo radio telescope in Puerto Rico, showed conclusively that the planet's rotational period was about 59 days. The theory that Mercury's rotation was synchronous had become widely held, and it was a surprise to astronomers when these radio observations were announced. If Mercury were tidally locked, its dark face would be extremely cold. But measurements of radio emission revealed that it was much hotter than expected. Astronomers were reluctant to drop the synchronous rotation theory and proposed alternative mechanisms such as powerful heat distributing winds to explain the observations. Italian astronomer Giuseppe Colombo noted that the rotation value was about 2/3 of Mercury's orbital period, and proposed that the planet's orbital and rotational periods were locked into a 3:2 rather than a 1:1 resonance. Data from Mariner 10 subsequently confirmed this view. This means that Schiaparelli's and Antoniadi's maps were not wrong. Instead, the astronomers saw the same features during every second orbit and recorded them, but disregarded those seen in the meantime, when Mercury's other face was toward the Sun, because the orbital geometry meant that these observations were made under poor viewing conditions. Ground-based optical observations did not shed much further light on Mercury, but radio astronomers using interferometry at microwave wavelengths, a technique that enables removal of the solar radiation, were able to discern physical and chemical characteristics of the subsurface layers to a depth of several meters. Not until the first space probe flew past Mercury did many of its most fundamental morphological properties become known. Moreover, recent technological advances have led to improved ground-based observations. In 2000, high-resolution Lucky imaging observations were conducted by the Mount Wilson Observatory 1.5-meter Hale telescope. They provided the first views that resolved surface features on the parts of Mercury that were not imaged in the Mariner 10 mission. Most of the planet has been mapped by the Arecibo radar telescope, with 5 kilometers (3.1 mile) resolution, including polar deposits in shadowed craters of what may be water ice.